Good afternoon, class. Here's elementary statistics, practice test number 5, module 5, covering chapters 10, 11, and 12. Here's chapter 12, analysis of variance. Reminding you when we take the exam, we pledge not to receive any assistance whatsoever. We may use formula sheet, tables, and a graphing calculator for statistics. So chapter 12, analysis of variance. One-way analysis of variance, short ANOVA, is used for tests of hypotheses that 3 or more populations have means that are all equal, as in H0, mu sub 1 equals mu sub 2 equals mu sub 3. In other words, we have more than 2 populations. By analyzing sample variances, one-way analysis of variance is used with data categorized with one factor or treatment. So there is one characteristic used to separate the sample data into the different categories. The populations have the same variance, sigma squared, or standard deviation, sigma. In the F test for analysis of variance, or ANOVA, 2 different estimates of the population variance are made. The first estimate is called the between group variance, and it involves finding the variance of the means. The second estimate, the within group variance, is made by computing the variance using all the data and is not affected by differences in the means. It helps answer, are the group averages different just by chance, or is there real evidence of a difference? Instead of comparing groups one by one, like using many t-tests, ANOVA does it all at once using variances. If there is no difference in the means, the between group variances will be approximately equal to the within group variance, and the F test value will be close to 1. Do not reject the null hypothesis. If the means differ significantly, the between group variance will be much larger than the within group variance. The F test will be significantly greater than 1. Reject the null hypothesis. So the F test. The ANOVA test is right tail test because only large values of the test statistic cause us to reject equality of the population means. Other statistical tests, Chaffee test and Tukey test, are used to find where the difference exists. Although the t-test is commonly used to compare 2 means, it should not be used to compare 3 or more. So in short, ANOVA, analysis of variance, is used when we have more than 2 samples, and it just tells us whether there is a difference or not. But where does the difference land? It doesn't indicate that. Here's an example we want to look at. Weights in kilograms of cypress trees were obtained from trees planted in a sandy and dry area. They were given different treatments as indicated. So no treatment, fertilizers, irrigation, fertilizers, as well as irrigation, both of them. Fill up the table, this table, below, and use a 0.05 significance level to test the claim that the 4 treatments, there are 4 categories, 4 treatments or factors, yield cypress trees with the same mean weight. So there is a lot of calculations involved. You don't do it by hand normally, but I'm going to show you the concept. And if we were to do it by hand, how it's done. So we have 1, 2, 3, 4 groups or 4 categories. Now, here are some of the formulas that you are familiar with, some you're not. For example, x bar is summation of x over n. Everybody knows that. S squared is summation of x minus x quantity squared over n minus 1. That's the variance that you calculate for a sample. And now this is new. X bar sub g, that means the grand total, and we're going to take it from there. There are other formulas. We discuss them as we go through them for the sake of filling up the table. The grand mean, this one, x bar sum g is the average of all the values when the factor is ignored. It is a weighted average of the individual sample means. So there are two ways to calculate it. One is just add them all up. Doesn't matter which group they belong to. Start from 0.24 all the way to 0.95, add them up and divide by a total space. The other one is that you average out the means for this group. Of course, if they have the same size, you just divide it by k. If not, you have to do the weighted average if the size is not the same. Sum of squares, SS, measures total variation by summing the square differences between each value and the mean. In other words, we are looking at the numerator here. That is called the sum of squares. There are two sources of variation. Between group variation SS sub b, which is summation of n sub I, x bar I minus x bar g quantity squared. The variation between the groups, SSB, or the variation due to the factor. It is the variation between each sample mean, so x sub I bar each sample mean, and the grand mean, x bar sub g or x sub g bar, or each individual variation is weighted by the sample size. It tells of the distance of the cell means from the grand mean. Okay, so the mean from each group from the grand. Within group variation, SSW, summation of x sub I minus x bar sub k quantity squared. The variation within the groups, SSW, or the variation that cannot be explained by the factor, so it's called the error variation, the error. The within group variation is the weighted total of the individual variations. The within group or within cell sum of squares come from the distance of the observations to the cell means and indicates error. The total sum squares, SS sub t, comes from the distance of all the scores from the grand mean, summation of x sub I minus x sub g bar quantity squared. Those are the information. Now, when you divide by a proper number, becomes a variance. Variances or mean square, also known as mean square, abbreviated by MS, mean square, and often with an additional variable, ms sub b or ms sub w, they are an average square deviation from the mean and are found by dividing the variation by degrees of freedom. For example, ms is in general SS divided by degrees of freedom, which we have here. So in other words, sum of squares would be the numerator, and when you are divided by the denominator, which is the degrees of freedom, it becomes a variance in each case. So this is the same question, this is the same table, and we want to see how to fill up these tables. We are going to look at some calculations. Okay, so how do we get to this and all these formulas? Let's start with count n sub I. So what does that mean? That means count. How many do we have here? 1, 2, 3, 4, 5. What is the sample size here? 5. Needless to say, the rest of them happen to be the same. So we're going to do for one of them, and the rest of them we repeat. They don't have to have the same sample size, but when they do, it makes the calculation easier. So that's the count or n or sample. So for the first group, we're going to call it n sub 1. For the second group, we're going to call it n sub 2, so on and so forth. Summation of x sub I, we're going to add them up. So the first group would be 0.24 plus 1.69 all the way to 1.8. And that would be summation of x sub I happen to become 5.95 for the first group. Average x sub I bar is summation of x sub I over n. So how do you take the average? The total that is 595, we've already calculated it, divided by the size, which is 5. So 5.95 divided by 5 would be the next one, which is 1.119. So we got the sum, we got the count, and this is the average of the first group. Now, sum of squares, SS, is summation of x sub I minus x bar sub k quantity squared. So for the first group, this k is 1, of course. So group 1, the first group, we are going to go with SS, and we're going to call it SS sub 1. For the second group, SS sub 2, so on and so forth. So how do you calculate SS sub 1? X sub I minus x bar sub k, that means for the first group. Okay, so that means 0.24 minus the average, 1.19 quantity squared, plus the second one, 1.69 minus 1.19 quantity squared, all the way to the last one, which is 1.8 minus 1.19 quantity squared, and that is SS sub 1, everybody. SS sub 1. So again, I'm showing you calculation, okay? Although I can't emphasize this enough, this is not done by hand. How do you calculate the variance? Okay. The variance would be this summation that we calculated divided by n minus 1. So this number divided by 5 minus 1, that divided by 4. Divided by 5 minus 1 or 4, we put it here. So we did the calculation for the first group one by one with details. We do the same thing for the second, third, as well as the fourth group. We fill them up. So I'm assuming everybody's okay with that. Now we're going to continue to the next page. So we have the groups and all these calculations from the previous page. This is the table we are supposed to fill up. And you remember all the formulas. Again, x bar is squared. I just want to make sure we understand that. So how does the calculation work? Again, I want to start with what we already showed work with details. Summation of x over n. That means start from 0.24 all the way add up to 0.95 and divide by, because each one is 5, 4 times 5 divided by 20. Remember, we get 1.0935. This is known as the grand total, grand mean for the total. Okay, and we call it x bar sub gm or g or t. There are 3 different ways of writing it. This could be gm, grand mean, just g or t. They all mean the same thing. So that means the entire groups, they give us a mean of 1.0935. In other words, don't treat them as individual groups. Just imagine it's entirely one group. Done. SSB, the sum of squares in between is n sub I, x sub I bar minus x bar sub gm quantity squared. So how do we calculate that? First, let's look at the first group. N sub I, the first group, n sub 1 is 5. It happened to be the same for all of them. So just the first group is 5. Then x sub I bar, the x1 bar is 1.19 minus the grand mean 1.0935. So 5 times 1.19 minus 1.0935 quantity squared. That would be the first one. Plus, we do the same thing here. For example, for this one would be plus 5 times 0.884 minus 1.0935 quantity squared and all the way to the end. So we do that all the way to the end. So there are 4 of them. And we get SSB, the sum of squares in between of 0.317295. So now we are ready to put something in this table. So in between SSB has been calculated. We put it here. So that's pretty straightforward, everybody, so far. The next thing is, let's fill up degrees of freedom, because in order to get to the next column, we need those, and we're going to divide what we find in this column by this column. Degrees of freedom, k minus 1, we have 1, 2, 3, 4 categories. K minus 1 is 4 minus 1. So this is 3. And then this is n minus k. Total, we have 20. And we have 4 groups. 20 minus 4 is 16. So this is 3. This is 16. They add up. This is the total. They add up to 3 plus 16 equals 19. This should be easy to understand. Okay. There are 4 groups. Okay. And that becomes the degrees of freedom for the numerator. And this is for the denominator. So having said that, let's go to SS. So let's calculate this MS, the mean square or the variance. So divide this number by this number. So SSB divided by K minus 1. So this number divided by 3 gives us 0.105765 goes here. Now we're going to calculate SSW, SS within, and again the formula is, there are 2 ways to write it. N sub I minus 1 times S sub I squared, or X sub I minus X sub K quantity squared. That means you just do them one by one, and it's easier to go with this one, N sub I minus 1. This happened to be 5 minus 1 for this group, and the same for each and every one of them. So N sub I, that means the sample size for a group 1, group 2, and so on, happen to be 4 for each one. So this one, 4 times S1 squared, plus 4 times S1 squared, this one, and the same thing. This is faster calculation. So 4 times 0.3916 plus 4 times 0.3905. Okay, I then put a 3 and so on. And that gives us the total sum within. And this is one way to calculate it. And you can do it individually in this manner as well. So we are going to put this number here. SS total, you really don't need it, but SS total, just add these 2 numbers. 4.659255, that's SS total, remember. That means if you do it for the entire set of samples, you calculate that. That would be the sum of squares. And now Going back to this one, we found this one. Now we want to find this one, which means the sum that we have divided by 16 is the answer. And when n sub I are the same, in this case, as you can see, they have the same size. So simply put, you can average out the S1 squared. In other words, if you add those four and divide it by 4, that will give you the same answer, 0.271373, and you put it here. So I'm showing you how the calculation works. And finally, for this table, this one, okay, you gotta put this one here. The ratio of these two is the F. So F is MS in between over MS in within, and that number is 0.3897. We put it here, everybody. And now we are actually ready to do the test of hypothesis. As you can see, the calculation is involved. You don't have to do this by hand. I can't emphasize this enough. But I wanted you to see that. So we are going to continue. Here's the given. Here's the information we calculated. Now we're going to do the test of hypothesis. In this case, we have 1, 2, 3, 4 groups. H0, mu1 equals mu2, all the way to mu sub 4. That is the claim. Now, H1, at least one of them is different, and we always take it to be RTT, right tail test. The second step is to calculate the test statistic, and this is the test statistic, everybody. We did calculate it. So test statistic, F is equal to 0.389741. Now, the next one is the critical value. Now, the table that we've calculated had this one. This comes from technology, but the methodology is very simple. Critical value comes from the choice of alpha, and then you have 2 degrees of freedom for the numerator as well as the denominator. I'm going to show you with the table on the next page because there's not enough room here. But as far as the degrees of freedom, we already know the degrees of freedom are 3 and 16. So this is the critical value. How would we get that? The number of groups K is 4. Degrees of freedom of the N numerator is 4 minus 1 or 3. The total size is N minus K is the degrees of freedom of the D denominator. With alpha of 0.05, the critical value from the table gives you 3.23887. From the table doesn't give you as many, you know, decimals, but you understand that is, of course, less when it comes with the table. It's not a big deal. It's close enough that will give you the answer as you need. All right. As far as the graphing is concerned, let's do the graph. And this is a 0.05. The critical value of 3.223, let's say 89 is here. And the test statistic is way into the non-rejection region. And if we were to do the p-value, by the way, would be this area, the area to the right of test statistic, F equals 0.3801. And that p-value, again, the technology has given it to us, which is larger than alpha 0.05. Both of them, whether we go with the critical value versus test statistic, the traditional method, or the p-value method, we get to the same result and fail to reject H0. So now we go back to the very first step. If we are not rejecting H0, we are not rejecting the claim becomes true, and then we restate as follows. There is sufficient evidence to support the claim that 4 population means are all the same. We conclude that the 4 treatments do result in cypress trees with the same weight. Okay. Now, again, reminding you how the test works. First, you need to know the alpha. Alpha in this is the table. You can find it online or in the module in Canvas. So first and foremost, you choose alpha 0.05. I can't emphasize this enough. Okay. So if the degrees of freedom for the numerator is 3, for the denominator is 16, you look at 3 at top, row 16, the left column, point of intersection is the answer, 3.239. Of course, class, of course, less decimals. It makes sense versus technology that gives you a lot more decimals. Given the readability score summarized in the following table and a significance level of alpha of 0.05, use technology to test the claim that the 3 samples come from population with means that are not all the same. So we have to use the technology because it's very hard to do it by hand. Okay. So first of all, understand there are 1, 2, 3 groups, and each one has n 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So n is 12 for each case. N happen to be 12 for Clancy, Rowling, and Tolstoy. Okay. Then we can add them up and divide by size for the average x bar and summation of x minus x bar quantity squared over n minus 1 for the variance. So we calculate the S, of course, is the standard deviation. This is again using calculator. Also, this table comes from, more specifically, it's from Excel. It can come from a TI calculator, makes no difference whatsoever. So we have 3 groups. So step 1, H0 mu sub 1 and mu sub 2 and mu sub 3 are equal. Okay. And whether we're checking that they are not all the same, so at least one of them is different, makes it right tail test and a claim. The next step is to calculate the test statistic, more specifically, look for the test statistic F and TS. Test statistic is, of course, found from the table. Okay. Now we want to go with the critical value, the p-value. We're going to look at both cases, and doing that, basically, we are going to use the table that is given. So clearly, just to let you know what you have, this is the test statistic, this is the p-value, this is the critical value. So we just use the test statistic. The critical value, we need 2 things. The degrees of freedom for the numerator is 2 because 3 groups minus 1 and 33. Total of 3 times 2 of 36 minus 3 is 33. And so this is the critical value. Again, alpha is 0.05. K is 3, so 3 minus 1 or 2. That's as far as the degrees of freedom for the numerator. For the denominator, total of 36 minus 3 is 33, and the critical value is obviously 3.2849. You can stop with 4 decimals. And if we go with a graph, clearly we see that critical value of 3.2849 is here. Test statistic of 9.4695 is way larger than that, and it's way into the rejection region. Also notice the p-value, 0.000562 is less than alpha 0.05. And that results in the same decision. This is in the rejection region. This is less than alpha 0.05. Reject H0. It's very straightforward. So we go back to make a decision about the claim. If we are rejecting H0, that means we are accepting H1 loosely put, and the claim becomes true. And we write, there is sufficient evidence to support the claim that the 3 population means are not all the same. We conclude that those books have readability levels that are not all the same. So If we were to do this by technology, everybody, one-way ANOVA clear list L1 and L2 and so on. In this case, we need three lists. And we're going to put the information and then ANOVA with L1, L2, and L3. So having said that, in L1, we have 58.2, 73.4, and so forth. In L2, we have 85.3, 84.3, and so on. And in L3, we put 69.4, 64.2, and so on. Okay. Now we just do ANOVA L1, L2, L3, and it gives us this. And notice the arrow. So we uh, get the rest of them. And now let's look at what is given to us. Notice here's the test statistic, this number, and here's the p-value. Please understand this means 5.621 times 10 to the power of -4. So these are the two values, okay? I hope you see that this means move this decimal to the left by 4 places. So this is scientific notation, everybody. Then look at this, okay? Sum of squares and MS, we have these two numbers. This is for in between. What about this one? Sum of squares for within 2331.38667, and the MS is 70.64, and so on. So as you can see, everything that we want is calculated using TI or Excel. We can easily come up with the answer. Needless to say, you don't have to do this by hand. You need to understand how it's done.